So we're going to prove or describe how to prove. We'll mostly write down most of what we need. The Ford, Fulkerson, and there's usually a bunch of other names attached to this, but these are the two that I'm most familiar with seeing. I have seen others though. Ford Fulkerson, this is the max flow. Min cut. Okay, so I'm just playing, I know because I'm playing games with parentheses and brackets, but these people did it. This is the name of the theorem that it's usually referred to as, and then I'll just state the theorem. Okay, so the V or A maximal flow in a flow network is equal to, in value of course, the capacity of A or the, if there's just one, minimal cut. Okay. In terms of sort of writing this in terms of an equation, you would say the max, right? So of all the flows possible is equal to the minimum, and this is for any ST capacity. Right, it's hard to kind of index this because flows can be put on there a variety of ways. We've done flow augmentation as a method for introducing flows and putting them on the graph. But that's not the only way to do it. You could actually, in theory, do this haphazardly. Throw a number on there, follow the consequences downstream and just make it work, and then do another one and try to make it work. And while this is depressing, I've seen students try to do that, and it's really hard to do. You could, in theory, do this, where you just throw flow numbers on there and hope they work out. If they work out, it's still going to be bounded, and in fact, the biggest one is going to equal the minimum cut capacity. All right, proof, again, this will be somewhat of a sketch, but we have most of the ideas assembled, so it's not hard to do. So kind of the first thing you do is you apply flow augmentation. Okay. Then until termination, sorry, let me note that, until it terminates. Basically, add as many flows as you can. Augment until you can augment no more. All right, and then you're gonna build ST cut, where S is the accessible nodes, of course, with the source, and T is the inaccessible. Okay. Okay. Then note the flow across this cut. We know by just the very basics of how flows and capacities are calculated is definitely not bigger than the capacity across this cut. But we can do better. We actually have, in this case, because we did flow augmentation and we made this particular division, we have the flow actually equaling the capacity. Because the flow on an edge is equal to the capacity of that edge on any edge going from S to T. And the flow on an edge is equal to 0 on any edge going backwards. Right, otherwise we could use backflow and that would have been an accessible vertex. So we have these two properties, and so that means that these two things are equal. Alright, since flow is equal to the capacity in this case, we know that the flow, let me just write this flow, is maximal, and I'll say max because that's short, and the cut is minimal. All right, and these facts are universal for any flow network. So this is always true. The max flow is equal in value to the minimal cut. And in fact, the proof is illustrative, but actually algorithmic about how to actually find these items, right? Find the maximal flow. It tells you also how to find the minimal cut. It also, the process even describes, based on how flow augmentation works, why these numbers actually have to be equal. It's completely intertwined with checking that you're done. Right? If you're checking that you're done, you're going to accidentally, whether you intend to or not, you're going to create this ST build here, this exact cut that has these properties where the flows across, going from the source side to sink side are full, and the ones going backwards should be completely empty. So you're just going to create that anyway. It's not like you have to make a special effort to do it. If you want to check that flow augmentation is done, you need to check, and that process is going to create this cut with these properties. Okay. All right, so that's the main thing to get away from this. It's not that you need to just start searching for a minimal cut. That is not step one. Step one is to do flow augmentation until you're done. Once that's done, you can then check to see if you're done, and in doing so, you will create this ST cut. All right, see where you can get. The stuff you can get to will be S. The stuff you can't get to will be T. And if you're done, of course, T should have the sink in it. If T has this, if you can still get to the sink, then you're not done. You do flow augmentation more. But then once you get to the point you can't get there, that's when all this applies. Okay, so that kind of completes this particular bundle of how to use flow augmentation. I will indicate kind of outside of this sort of video medium some applications of flow augmentation that go beyond just finding maximal flows in networks, so you're not doing it in a vacuum, point to scheduling problems, and a few other things that you could be interested in doing. There's a lot of applications beyond just the sort of the silly, let's maximize flow on this graph for no reason whatsoever. All right, so I will see y'all in the next videos.